Hello everyone, I am Amritpal Singh Chaddha, working as a technical assistant in Birbal Sahni Institute of Paleosciences. I am having ample experience in X-ray diffraction and its methodologies. In today's module, I'll be your teacher and will teaching you the basic principles of X-ray diffractions and its implications in the geochemical analysis. Now, after this useful session, the learner will be able to understand the basic concepts of XRD, describe the process of generation of X-rays, define the diffraction and the Bragg's law, analyze the XRD facility at the BSIP, portray the instrumentation of XRD and explain about the various X-ray detectors. And finally, the learner will learn the numerous applications of the X-ray diffraction. Now, in 1665, diffraction effects were observed by Italian mathematician Maria Grimaldi. In 68, X-ray discovered by the Röntgens. In 1912, X-ray diffraction by crystals was done by one law, and in 1912, Bragg discovered the Bragg's law, which is very useful nowadays. Now, where the X-rays lies in the electromagnetic spectrum, user can easily see that X-rays are on the higher frequency sides in 0.01 nanometer to 10 nanometer range. Now, how X-rays are generated? X-rays are generated in a vacuum sealed tube where the tungsten filament is there. When the voltage is applied, the electrons from the thermoionic effects will pass from the tungsten cathode to the anode, which generally is copper in our case, and X-rays are generated. Now, I'll be showing you the mechanism of X-ray production. Now you can see that the thermoionic electron is coming and it hits the K shell of an atom. Now, the electron from the K shell escapes and the electron from the L shell takes its position, leading to the energy which is called K alpha. And secondly, if electron hits again to the K shell and electron from M shell falls, the radiation will be K beta. And these radiations are characteristic radiations which are very useful in the spectrum. Now, what is the energy which is required for the characteristic radiation? It is given by the formula Hc by lambda Kh. Now, user can see that this is the spectrum of the X-ray generation. It moves from the continuous to the characteristics and to the short wavelength X-rays. For our purpose, characteristic radiations K alpha and K beta is very useful. So, we use filters such as nickel for the continuous spectrum. This is all about generation of the X-rays. Potential difference is applied, cathode is the source of electron, anode is the charged target of electrons, and electron released from the cathodes are accelerated towards the anode by the potential difference, and around 99% of the kinetic energy is converted to the heat via collisions, and only 0.251% of the kinetic energy is converted to the X-rays via Coulombic interactions. Now, what is diffraction? Diffraction is the beam composed of large number of scattered rays mutually reinforcing each other. So, how is diffraction different from the reflection? Diffraction is a subsurface phenomena and reflection is the surface phenomena. Diffraction occurs at only specific angles, whereas reflection can occur at any angle. Now, what is Bragg's law? Bragg's law states that the incident beam, the normal, and the reflection plane and the diffracted beam are always coplanar, and the angle between the diffracted beam and the transmitted beam is always 2 theta. Please note that the lambda should be less than twice the d spacing we want to study. There are different methods of diffraction which depends upon various factors, whether the wavelength is fixed or variable. So, Lau gives the method in which he states that the wavelength is variable, and angle is fixed. Generally we use it for the single crystals. And methods such as powder method, which we are using generally in our mineralogy purposes, the wavelength is fixed and the angle is variable. The specimen should be powder. This is the general layout of the powder diffractometer, in which the source is there, specimen is there and the slit is there. Generally it is called Bragg and Brentano geometry, where generally stage is fixed and source and the counter detector is moved to the various appropriate angles. This is the setup of powder XRD at the BSIP, in which the X-ray gun is there, sample holder is fixed and detector is there. X-ray guns and detector moves appropriately. As you can see, diffraction pattern are of various intensities and various natures. You can see the crystal will give very sharp diffraction pattern in comparison to the amorphous material. Most of the material and their peaks are easily documented, generally JCPDS and ICDD. Now I'll be talking about the instrumentation part. This is the powder XRD in the Birbal Sahni Institute of Paleosciences. We are using Expert 3 powder diffractometer. So what are the essential parts of a diffractometer? It should have a source, optics and the detector. As you can see, we have a vertical configuration, which means we have a horizontal sample and we have theta to theta movement, means source and the detector will move and the sample is fixed. This is how is the general layout, how the tube looks like. The cathode is there, it will emit electrons thermoionically and it falls on the copper anode having 1.54 Armstrong wavelength, and X-rays are emitted out of the beryllium window. This is generally the layout of the X-ray tube. This is the goniometer, which is a stage where the source and the detector moves to various angles. So, if in easy way I will tell you, X-ray tube is the source, incident beam optics are there, goniometer is there, which is the platform which holds the source and detector, sample holder is there, receiving side some optics will be there to condition the beam, and finally detector will be there to amplify the signals. As you can see, we use parafocusing method for diffraction purposes of powder methods, because in the powder the crystals are oriented in every direction and only those directions which will follow Bragg's law will be oriented. So how this parafocusing is suitable? It is suitable for Bragg-Brentano geometry, powder diffraction, and when the X-rays are diverging. Various components are there such as filters, slits to be parts of the optics. As I have earlier told you, filters are there to remove the continuum part of the X-ray source, as we only need the characteristic radiation such as K alpha and K beta. Slits are there to limit the divergent X-rays, and narrow slits are there to lower the intensity. Now we will talk about X-ray detectors. Now we will talk about X-ray detectors. Usually, X-ray detector detects individual photons which we measure and wish to measure, such as energy, number, time of arrival, position and polarization. These all are the properties which detector measures. I'll just talk about two basic detectors in my talk, solid state detectors and pixel detectors, which is a form of charged coupled diode detectors which people in modern ages are using. In solid state detector, X-ray interacts in material to produce photoelectrons which are collected by the applying drift field. Next, pixel detectors. These are the form of charged coupled detectors in which there is a good energy resolution, single readout electronics are there. Pixelated detectors have very large pixel sizes which does not require many electronic channels but are very fast, and high resolution peaks are there. Now we will see what are the applications of XRD in the geology and geochemical point of view. In the XRD, as we know, we can know the crystalline and amorphous nature of the material. We can know the bulk mineralogy of the sample. We can separate the clay from the bulk sample, and we can know what are the clays are there. We can know the stress, strain using the Debye-Scherrer equations, and we can use the quantitative methodology also, how much amount of mineral is present in each sample. So, characterization of crystalline minerals, clay analysis such as montomonolite, chlorides, kelonites can easily be done through XRD. Quantization of amount of minerals also can be done, and finally, the XRD can be helpful in indicators of the geographical history. Finally, I hope my talk was very useful to the listeners and it has benefited you in the different ways in learning the basic principles of XRD and its implication in the geochemical perspective. Thank you for patiently listening to me. I hope in future I will be giving you more talks. Thank you. Hello everyone. I am Amritpal Singh Chaddha, working in the XRD lab. I take care of this XRD lab in the Birbal Sahni Institute of Paleosciences. As I have told you in my theory class, now I will give you the practical feel of the XRD instrument. We are using a pan-analytical expert 3-powder instrument which uses source of the copper, and using the Bragg-Brentano geometry, the sample stage is fixed and the detector is variable. There are two types of powder holders which we are having. One is for bulk samples and another one is for the clay slides. Now I will show you the practical working of the instrument, how we operate it safely. For the safety purpose, we generally use the counter of Mazur, which is the GM counter. We generally look out the external radiations so the operator or any person working in the lab feels safe. So this is the clay slide which I am putting into the diffractometer. This is the sample stage. Slowly we will put the sample onto the sample stage and we'll close the windows. Now as you can see, the diffractometer has started. Now slowly by the angles, it will give the data to the analog circuit by the computer. As we have variable scan rates, you will be seeing that this is a high resolution scan from 24 theta to 26, and now you will get the live spectra onto the computer screen. As you can see, the shutter is open and the X-rays are coming out. This is the lead glass which we use, and you can see on the on display the theta and the 2 theta variations. Now as you can see, you are getting a spectra which is the intensity on the left side, and on Abesica it is the 2 theta. So this is the high resolution scan of one of our samples. As from the spectra, you can see the molecule is not perfectly crystalline as the peak is broadening. It is having the amorphous nature. Thank you viewers. Signing off from my side, Amritpal Singh Chaddha. Hope you have seen and feel the hands-on experience onto the XRD instrument. Thank you again.